In the last lecture, we have seen that Rn D is a complete metric space. Under the metric D, define as sigma mod xi I minus eta I whole square I is 1 to n under root, where x, which is xi 1, xi 2, xi n, and y, which is eta 1, eta 2, eta n, are the points of Rn. We will go few more examples where the metric space also comes out to be a complete one. So, another important example is L infinity space under the metric D infinity is a complete metric space, where L infinity, as we know, is the collection of those infinite sequences xi such that supremum of mod xi is finite, that is set of all bounded sequences of real or complex number. And the notion of the metric which we have introduced as d infinity x y as the supremum over I mod xi I minus eta I, where by is a sequence by eta 1, eta 2, eta n, and so on up to infinity. X is xi I is 1 to infinity, y is eta I is 1 to infinity, both are the elements of L infinity. We claim that this is a complete metric space. So, it means if we prove that every Cauchy sequence in L infinity is a convergent one, limit point belongs to the L infinity, and the convergence is in the metric of D infinity, then it is a complete metric space. So, the proof goes like this. Let us consider an arbitrary sequence x n which is Cauchy. So, let x m, which is say xi m I is 1 to infinity, be a Cauchy sequence, do not put this bracket, okay, be a Cauchy sequence in L infinity, be a Cauchy sequence in L infinity. So, by definition of Cauchy sequence, we get for given epsilon greater than 0, there exists an n depending on epsilon such that for m r greater than equal to say capital N, the d infinity of x m x r is less than epsilon for m r is greater than equal to n. This we have mentioned earlier. It means the supremum over I mod of xi I m minus xi I r is less than epsilon for all m r greater than equal to n. This implies that for each I, for each fixed I, xi I m minus xi r is remains less than epsilon. Clear? And this is true for all m r greater than equal to n. It means, if I consider the sequence like this for fixed I, if I consider a sequence like this xi 1, xi 2, xi 3 and so on. Now, this sequence has a character, the difference between any two arbitrary terms of the sequence after a certain stage, say capital N onward, remains less than epsilon. Is it not? Because here it will be the term xi to the power m, xi to the power m plus n plus 1 and so on so forth, but for which this is true. So, it means this is a sequence which behaves as a Cauchy sequence of real or complex number for each I. So, for fixed I, if this sequence behaves as a Cauchy sequence of real or complex numbers, and any sequence which is Cauchy, real sequence or complex sequence which is Cauchy is a convergent one. So, this sequence for each I, the sequence xi I m converges is a convergent one. Clear? Is convergent, therefore, we can say xi I m tends to xi I as m tends to infinity. Okay? Now, let us pick up this again. From this result, mod of, so since x m we have taken as xi by n m, xi 2 m, xi n m and so on. As m tends to infinity, xi 1 m will go to xi 1, xi 2 will go to xi 2, xi n will go to xi and so on. So, correspondingly we get a point x. Clear? Once we get the point x, then this will be the limit point of the sequence x m, which tends to x when m tends to infinity. Now, if this point x belongs to L infinity and this convergence is in the metric of L infinity, then L infinity will be complete. Okay. So, first to show that x m, this x belongs to L infinity. Okay. Now, how we get by previous year supremum over I mod xi I m minus xi I r, this is less than epsilon r for m r greater than equal to n. Clear? Therefore, for fixed for each I xi I m for each I, and let r tends to infinity, fix m. Then what happen is the xi I m and xi r will go to xi I, will remain less than epsilon r for m greater than equal to n, for those m which are greater than equal to m. Now, this is true for each I. So, supremum of this thing will remain less than epsilon r for m greater than this. This is I, but this supremum, this is nothing but the d infinity x m x. Therefore, this x m converges to x in the metric of d infinity. Is it okay? Now, if x belongs to this class also, then it is fine. So, to show the x belongs to this class, because if we get here, since xi I, we can write it as xi I minus xi I m plus xi I m. So, mod of this is less than equal to mod of this plus mod of this. Now, this part is 10 less than epsilon r, and this sequence x m is in the point of, this is less than epsilon r plus k m, where k m is the supremum of mod xi I m over I. Because x belongs to x m, this belongs to L infinity. Therefore, this must be finite. So, once this is finite, then we can say that each term of this will remain less than equal to k depending on m, k suffix m. So, this is constant, this is also constant, and it is independent of I. Right hand side is independent of I. So, take the supremum and we get from here the supremum mod xi is finite. This implies our sequence x, which is xi, is in L infinity. Okay. So, the xm converges to x, the limit point x belongs to L infinity, and the convergence is in the metric of L infinity. Therefore, L infinity d infinity is a complete metric space. Is a complete metric space. Okay. So, this is very easy to show the completeness. Sometimes you have to use a different lines of proof to show the completeness, and that gives you a simpler way method. For example, if we wanted to show completeness of C, what is C? C is the set of all sequences x, say xi, which is convergent. Set of all sequences which are convergent sequence. Okay? So, all convergent sequences are there. Every convergent sequence is a bounded sequence. So, obviously, it is a subset of L infinity, and the same metric we can introduce on C. So, we can define on C the metric d infinity. Okay. Same metric we can introduce it. Now, our aim is to show that C under this d infinity is a complete metric space. Complete metric space. Clear? Now, here we will use a different trick, different line of proofs to show this is complete. The advantage in this problem is, because it is given that C is a subset of L infinity, it is known L infinity is a complete metric space. So, since C is a subset or subspace of a complete metric space, L infinity. So, there is a lemma which we have proved that any subspace of a complete metric space is complete if and only if it is closed. So, C is subspace of complete metric space. So, it is required to prove only that C is closed. C is closed in order to show C d infinity is complete. This is why C is closed means required to prove C is equal to C bar. C is closed means it must be equal to its closure, but C is already a subset of C bar. So, it is remain to prove that C bar is a subset of C. So, entire thing is now reduced to only one part, that if I prove that C bar is a subset of C, then C will be a complete metric space. So, in order to show C bar is a subset of C, we will pick up a arbitrary point in C bar, and then we say that point belongs to C, then our result is complete. So, let x belongs to C bar, but C bar is a closure of the set C. It means either x will be a point of C or x will be a limit point of C. If x is a point of C, then nothing to prove, because it is already. So, if x belongs to C bar, it means there exists a sequence, say x n, x n in C which converges to x. Is it not? There exists a sequence x n in C which converges to x. So, that is what we get is that for given epsilon greater than 0, there exists an n such that d of x n x remain less than epsilon for all n greater than equal to capital N. Is it not? Let it be this in place of epsilon, let it be epsilon by 3. Now, this is true for all n belongs to greater than equal to n. So, in particular d of x n x will remain less than epsilon by 3. It means the sequence x n that is equal to x n x 1 x n which is x 1 n x 2 n and so on is a convergent sequence. Is it not? Because it converges to x, it is a convergent sequence. Every convergent sequence is a Cauchy sequence, but every convergent sequence is a Cauchy sequence. So, this has also be a Cauchy sequence. So, for given epsilon greater than 0, there exists a some number capital K such that d of x this is a convergent sequence. So, we can say d of x j n comma d of x k n remain less than epsilon for all j k greater than equal to capital K. Is it not? For all j k greater than equal to capital K. So, let it also be this epsilon by 3. Is it okay? Now consider the point we wanted the limit point x n converges to x. It means that x this sequence x which is a must belongs to the class C, that is x must be a convergent sequence. So, if I prove that x is a Cauchy sequence of real complex number, then it has to be convergent. So, start with x j x j, I am taking x j, is it not? So, start with x j minus x k. Now, this part can be written as x j minus x j n plus x j n, let it bracket use bracket. Okay. This is x n minus x k n and then plus x k n minus x k. Okay. Now, x j is a Cauchy sequence. So, from this the middle portion becomes epsilon by 3. Okay. The first portion becomes less than epsilon by 3 because of this. Last portion also becomes epsilon by 3 because of this. Okay. So, this is less than equal to epsilon by 3 plus epsilon by 3 plus epsilon, and this is true for all j k greater than equal to k. So, the sequence x j, so the sequence x j which is say x is a Cauchy sequence of real or complex numbers, but it is convergent. Therefore, x which is x j is a convergent sequence. Therefore, x belongs to C. So, x we have started in a point C bar and shown that x belongs to C. It means C bar is a subset of C. So, this implies C is equal to C bar. Therefore, C is a complete metric space. Okay. So, this is the different way we have shown that the advantage was here because the space which we have chosen is basically comes out to be a subspace of a complete metric space. If L infinity would not be a complete, then we cannot use this criteria. Okay. Another example which we frequently use, the LP space. The LP space under the metric dp is a complete metric space, is a complete metric space. Okay. The line of proof is almost same. So, I will just skip the few parts, only the portion from where it is required we will show. So, what is the proof is, let x m, which is xi m, be a Cauchy sequence in LP. Okay. So, once you get this, it means the dp xm xr remain less than epsilon r for mr greater than equal to n. Just for a given epsilon r we can find this, but how to define that dp? dp, if you remember, this is j I equal to 1 to infinity mod of xi j or j is 1 to infinity xi j m minus xi j r xi j r power p power 1 by p is less than epsilon r. This is the metric for all mr. So, from here if I remove the sum, then for each j this total sum less than epsilon r, and again this is a sequence of real or complex number which is Cauchy. Therefore, it must be for each fixed j, it is a Cauchy sequence. So, we get from here is for each j xi j m minus xi j r, this will remain less than say epsilon 1. Okay. For all mr greater than equal to n. So, this is a Cauchy sequence. So, this sequence xi j m for fixed j, for each j or for fixed j is a Cauchy sequence of real or complex numbers. That is important. Therefore, it is convergent. So, it converges to a point x which is xi j as m tends to infinity. Clear? So, we are getting a point x as xi 1, xi 2, xi n and so on. This is the point. Now, whether this point belongs to L infinity or not, that is important. If it belongs to L infinity and convergence is in the metric of dp, then again L infinity dp L, sorry, it belongs to LP, and under the metric dp this convergence is there, then we say the LP dp is a complete metric. So, to show this is an LP and the convergence in dp, we start like this. Sigma, just a previous one, this j is 1 to infinity, this is less than epsilon r. So, if I truncate, say start with j equal to 1 to m or 1 to say n, then obviously this remain less than epsilon r. So, start with sigma j equal to 1 to n, not m, 1 to n mod of xi j m minus xi j r. Okay. This remain less than epsilon r to the power p, and here is p. Okay. Let us fix m and let r tends to infinity, fixed m. So, and this is true for m and r greater than equal to n. So, I am not touching m, let r goes to infinity. So, this xi j r will go to xi j. So, we get I is 1 to n xi j m minus xi j power p is less than epsilon r power p for m greater than equal to n. Now, let n tends to infinity now. So, when n tends to infinity, it is the I is 1 to infinity mod xi j m minus xij power p is less to the power 1 by p is less than epsilon for m greater. But this is nothing but the dp x m x by definition. So, we get x m converges to x in the metric of dp. Okay. Now, to show x belongs to LP, we now start with this. So, now what we want is the limit point x belongs to this belongs to LP. This we wanted to show. Okay. We have already seen that this sigma, say I is 1 to infinity, I is 1 to infinity mod of x I m minus x I say raised to the power p is less than epsilon to the power p. That is a sequence x n m, that is a sequence x m goes to x as m tends to infinity. This we have seen already. So, using this not only x m I, this x m minus x, this will be a point in LP, because the power sigma of this thing power p is bounded. This is all. So, this belongs to p. Now, consider mod x I j, which is mod of x I j minus x I j m plus mod of x I j m. So, it will come less than equal to sign. Now, since x m, which is a sequence x I j m, this is in LP, this sequence is also in LP. Therefore, by an LP is a linear space. So, by using the Minkowski inequality, one can easily show that this sequence x I j is in LP because of this. Okay. So, if I apply the Minkowski inequality over this, take the power p summation and then apply the Minkowski, we get this is in LP, and this proves the result of that LP under this metric dp is complete. Thank you. A same space may be complete in one metric, but if I change the metric, the same class of elements, same class may not behave as a complete metric space. For example, if we take the CAB, set of all continuous functions, set of all continuous functions, say x t, defined over the interval a b. Okay. This is our CAB. The metric, we can introduce the metric in two ways. One is d 1 x y as the maximum of mod x t minus by t, t ranges from this. And another way metric is introduced like this, integral a to b mod x t minus by t dt. Both are well defined because the function is continuous on a closed interval. So, it will attain its maximum value. So, therefore, this is well defined. Every integer function which is continuous is an integrable function on a finite interval. So, it is also well defined. So, both the metrics are well defined on CAB and they satisfy all the property of the metric space. But this CAB under the metric D 1 is a complete metric space, while CAB under the metric D2 is not complete, metric space. Class, I am not changing the class, just I am changing the matrix. With one metric it forms a complete metric space, while with other metric it forms an incomplete metric. So, the completeness of a space depends totally on the metric. Okay. If I change the metric, the completeness may be lost. Okay. So, let us see the proof. I think first part proof does not require much, that C A B under D1 is complete. This we want. So, start with the Cauchy sequence. Let X m be a Cauchy sequence. In CAB. So, by definition, so for given epsilon, there exists say m such that D1 x m x r is less than epsilon, but by definition this is the maximum of x m t minus x r t is less than epsilon, where t varies from a to b. Now, maximum value we are taking, since function x m and x r both are continuous, difference of this will remain continuous. So, maximum value we attain. So, there exists a t naught. So, there exists a t naught in the interval a b, where the maximum value will be attained. Is it clear? And this is true for what? For all m r greater than equal to n, for all m r greater than equal to n. It means this sequence x t naught x m t naught, this is a sequence. Now, when you are taking x m t naught, it means the x m is a function, value, the value of the function is taking at a point t naught. So, it is a real number, because CIB is the set of our continuous real valued continuous functions. So, it is a real number. Now, this real number satisfies the criteria that difference between any two terms of the sequence after certain time, after certain step remains less than epsilon. It means this is a Cauchy sequence of real numbers. Agreed? Once it is Cauchy, so it must be convergent. So, x m t naught is convergent, and it will converge to a point say x t naught. Okay? That converge to x t naught. Now, whether this x, whether this is a continuous function or not, if it is continuous, it will belongs to CAB. If it is not continuous, it cannot belongs to, but we claim that this will be a continuous function. Why? If we look the 1, the 1 is given the maximum of x m t minus x r t is less than epsilon. It means for all t, differences of this is less than epsilon. Clear? So, it means this less than equal to is true for all t. Now, if I take m fixed and r tends to infinity, then you are getting here is x m t minus x t is less than epsilon, but this is true for all t, and it means x m converges to x uniformly from here, from 1 let r tends to infinity. Okay. So, what we get is the maximum of t is less than epsilon for m greater than equal to n. Now, does it not imply that from here we can say that x m t converges to x t as for all t all t and m is greater than equal to n, or as m tends to infinity. Agreed or not? It means that it is independent of t. So, the sequence xmt xm converges to x uniformly over the interval a b. It does not depend on t, though it is from here we have seen it is a pointwise convergent, but basically because of the maximum it converges for every t. So, you can say it is uniformly convergent. Now, there is a result: if a sequence x n is a sequence of continuous function and it converges uniformly, then limit point has to be a continuous function. Okay. So, x m converges to x uniformly and x m is a continuous function, is a sequence of continuous function So, the limit function x will be continuous. That result is standard in the real analysis. Okay. So, if you want I can give the proof where we need, otherwise it is available in the book that if a sequence x n which converges uniformly and the sequence R of continuous function, then the limit function has to be a continuous function. So, this implies x is a continuous function. So, x must be in C A B and it converges to, and also this, and also x m converges to x in the metric of C A B, that is D 1. Clear? So, C A B under D 1 is complete. Complete metric space. Okay. Now, see the second part, that C A B under D 2 is not complete. Is not complete. It means that every Cauchy sequence in this class metric is not a convergent one. Okay. So, first we have to identify a sequence which is Cauchy, but it does not converge to a point of C A B, that is the limit point comes out to be a discontinuous function. Okay. So, let us see this at C A B. So, let x n be a sequence or x m be a sequence defined as in below. Okay. Defined as below. We define x m t equal to 0. Now, is not for the sake of proof, let us assume interval a b is identical 0 1. Suppose I prove this result for 0 1, then it can be extended to a b. Okay. So, let us introduce this as 0 if t belongs to the interval 0 to half and equal to, as in the figure, if it is t belongs to half, close half, and a m points, a m, where a m is equal to half plus 1 by m. This is in figure is like this, that suppose this is 0, this is half, this is a m, this one is 1, here it is 1. Okay. So, function is going like this, it is like that. So, between half to a m the curve is this, and then from a m to 1 again the curve is the value of x m t is 1. I am introduced like I have introduced the x m as well. Now, this x m is a continuous function, there is no point of discontinuity at all, clear. We claim this x m is a Cauchy sequence, is Cauchy in the interval C 0 1 under D 2. D 2 is a metric. Okay. Why it is so? Because if you look this again 0, here it is half, this is m, here it is say 1. Suppose m is greater than n. So, 1 by m will be less than 1 by n, it means a m will be less than a n. Okay. Here it is 1. So, this will be this and then this. Okay. For n it will be like this and so on, is it not? This is our a n and is it okay? Clear? So, basically no, this 1 by this is this will not be there. Okay. Because half to this, the figure is this, a n will be from start from here, a m will start from here and will go like this, a and this, is it not? This is our a m, okay, and this will be our a n, clear. So, this portion is there. Now, when you take the d of d 2 of x m x n, what happens? 0 to half both are equal. So, integral 0 to half will be 0, then no. From n onward again it both are same, only the problem will come between half n and m, is it not? Now, as n and m both goes to infinity, when both goes to infinity, a m coincide with half, because a m is half, a n will also coincide with half. So, basically both these figure will coincide to half and there will be directly jump here and we get this point, clear. So, basically this tends to 0 as n tends to, agreed. So, it is a Cauchy sequence, is this clear or not? Okay. What is this? Let me see, take this is our, okay, then this will be and this will be, okay, this one. Now, is it not this one is 1 by m, this is 1 by m, okay, 1 by m, this one will be 1 by n, is it okay or not? 1 by n, clear. Now, when you take d of this, what is this relation? 0 to half plus half to am, am to n to 1, n to 1 it is 0, difference will be 0, here it is 0. Okay. Now, these two things are there. Now, when n and m goes to infinity, a n is half plus 1 by n, a m is half plus 1 by m. So, when n goes to infinity, m goes to infinity, a n will coincide with half. So, this part will be 0. When n and m goes to infinity, both is half half. So, again this is 0. So, total will go to 0, clear. So, that is why it total tends to. So, it is a Cauchy sequence, clear, okay, but it is not converging towards continuous function. Why? Because if we look this, suppose let x n converges to a point x under the metric D 2. Suppose this be our assumption. Okay. Then what happens is D 2 x m x. This is equal to 0 to half, okay, mod of x m t minus x t dt plus half to a m mod of x m t minus x t dt plus a m to 1 mod of x m t minus x t dt. Is it correct? Okay. Now, this is 0 to 1 mod x m t dt x t 0 to half. What is x m t? X m t between 0 to half is 0. So, this is basically 0 and only thing left out is x t dt plus half to m means half plus 1 by m. Okay. Let it be like this, x m t minus x t dt, I am not changing, and here is a m will be half plus 1 by m and 1, the value of x m t is 1 minus x t dt. Agreed? Now, let m tends to infinity. The left hand side tends to 0 because we are assuming x n or x m converges to x. So, left hand side will go to 0. So, right hand side has to go to 0. So, right hand side has to go to 0, is it not? Now, in order to get it 0, the middle part is already 0. When m tends to infinity, this middle portion is already 0, because both upper and lower limit coincide. So, whatever the integrand may be, it comes out to be 0. Okay. Now, 0 and half both the positive limits and integrand is also positive. So, in order to get this to be 0, what is required is here the x t must be 0 when t lying between t belongs to 0 and half, is it not? And here again this is non-negative, limits are non-negative. So, x t must be equal to 1 if t belongs to half and 1. So, what you get? The x t comes out to 0 between 0 and half and 1 when half and. So, it is like this, that this is half, this is 1. The function is coming like this and all of a sudden it had a jump. So, there is a point of discontinuity at half. Therefore, x t is discontinuous, is not continuous at x equal to at t equal to half. Okay. So, if it so x cannot belongs to C 0 1, therefore, C 0 1 is okay. So, x does not belongs to C 0 1. Therefore, C 0 1 under metric D 2 is not complete. Okay. So, this completeness is also a property which depends on the metric. Now, there are another matrix, there are many spaces which are incomplete metric space. So, there are few more examples of the incomplete metric space. Let me see incomplete metric spaces. The first one is rational number. This is incomplete, okay, because you can find the real number r on the real line. If I take the limit of the sequence of rational comes out to be real, which is not available. So, it is incomplete. Second example, set of all polynomials okay, of degree say n. This is also incomplete. Why? Because the limit point of this set of polynomial may be a entire function, like for example, e to the power z. We know the series is 1 plus z square by factorial 2, z cube by factorial 3, z n y factorial and so on. So, if we take this as a polynomial What is the limit point? Limit point comes out e to the power z, which is not a polynomial, which is not a polynomial. So, set of all polynomials which are continuous functions does not form a complete metric space. Okay. So, there are many more examples you can find out which are incomplete. So, next class we will see, since the completeness also plays the role and in development of these functional analysis tricks. So, can it be possible to find out an structure which gives you a complete metric space out of incomplete one. So, we will discuss those things, how to find out a completion of an incomplete metric space. Thank you.